In previous lecture we have proved that every compact subset of metric space is closed and bounded. Converse of this result may not be true. Okay. So what we proved last, every compact subset of metric space is closed and bounded. Converse is not true, means closed and bounded subset of metric space need not be compact. Note, converse is not true. Is not true. That is, closed and bounded subset of metric space, closed and bounded subset of metric space need not be compact. For example, let XD be infinite discrete metric space, and A be infinite subset of X. Then A is closed and bounded. A is closed and bounded subset of X. As every subset of discrete metric space is closed and D of xy less equal 1 for all xy belongs to X. Now, since compact subset of discrete metric space is finite, since compact subset of discrete metric space is finite, and here A is infinite, implies A is not compact. A is not compact. So from 1 and 2, A is closed bounded subset which is not compact. Okay, from 1 to A is closed and bounded subset of XD which is not compact. So you can take X itself which is closed and bounded but it is not compact metric space. Okay. Now today we will state Hein-Borel theorem in R. A subset of, let RU be usual metric space. Then subset of RU is compact if and only if it is closed and bounded. Okay. So what is the theorem? A subset of RU is compact if and only it is closed and bounded. In general, closed and bounded subset may not be compact, but with respect to usual metric defined on R, every closed and bounded subset is always compact. Okay, so this for that one. Okay, let Rn n greater equal to be metric space with usual metric, then subset A of Rn, is compact if and only if A is closed and bounded. Okay. Extension of that for general metric space Rn with respect to usual metric. Now we will see the concept of totally boundedness. Boundedness. For this, first we will talk about epsilon net or epsilon net. Okay. Definition of epsilon net. Okay. So let XD be metric space and then for epsilon greater than 0, a subset A of x is epsilon net for x if x is equal to union of S epsilon A where A values in A. That is if every point of x is within a distance less than epsilon, every point of x is within distance epsilon from some point of subset A. If A is epsilon net for x, then it is also known as A is epsilon dense in x. If A is epsilon net for x, then A is epsilon dense subset of x. Epsilon dense. Okay. Now depending on this, we will define concept of totally boundedness. totally boundedness. A metric space XD is totally bounded if for given epsilon greater than 0, X has finite epsilon net. If for given epsilon greater than 0, X has a finite epsilon net. That is, for given epsilon greater than 0, there exists finite subset A is equal to say A1, A2 dot dot up to AN of X such that X is equal to union of S epsilon A, where A varies in AI, where AI is varies in A. AI is varies in A. Moreover, a subset Y of X is totally bounded if of metric space XD is totally bounded if YD is totally bounded subspace. YD is totally bounded subspace. Okay. Observe that here each S epsilon AI is bounded subset. Diameter of each epsilon open sphere is 2 epsilon. Okay. So by 1, diameter of S epsilon AI is less than 2 for area AI belongs to A. Implies each S epsilon AI is bounded subset of X. Now, since finite union of bounded subsets of X is bounded, finite union of bounded subsets of X is bounded implies X is bounded. Implies X is bounded by 1. Okay. And this implies each totally bounded metric space totally bounded metric space XD is bounded. Converse need not be true. Okay. Totally bounded metric space is bounded. Okay. Converse is not true. Is not true. That is, bounded metric space need not be totally bounded. Totally bounded. Example, let XD be infinite discrete metric space. Infinite discrete metric space. Then d of xy is less equal 1 for every x, xy in x, implies xd is bounded. xd is bounded. Now for epsilon is equal to half. For epsilon is equal to half, yes, half A is equal to singleton A. For any A belongs to X. Therefore, for finite subset, for any finite subset, A is equal to A1, A2, dot dot up to An of X, yes, epsilon or union of yes half AI belongs to A is equal to just A, not equal to X, implies X has no 1/2 net. X has no finite 1/2 net. And therefore, X is not totally bounded. X is not totally bounded. So what we proved here, every totally bounded metric space is always bounded, but bounded metric space need not be totally bounded. Bounded metric space need not be totally bounded. Is it clear? So with the discussion, we'll stop this lecture here. Thanks for listening lecture carefully. Bye bye.